Let's mix some ingredients and make some rocks. Here we have two magma chambers, magma chamber A, where some minerals are beginning to crystallize, and the intrusion of magma chamber B, which is of a more basaltic chemistry. Partial melting is going to create a magma of a particular composition here, and that composition is going to be the result of initial magma combined with some country rock. Cooling is going to cause the minerals to crystallize and settle, as we talked about a minute ago. Maybe some plagioclase laths forming here, and then sinking to the bottom of the magma chamber where they're going to fuse to other plagioclase crystals. Magma chamber B breaches magma chamber A and introduces its chemistry into the mix. So if this is your sourdough starter, this is your additional feeder material. The basaltic magma breaks through, the ingredients mix, and the result is we have an intermediate magma now. Intermediate magmas would produce andesitic rocks, named after the Andes Mountains in South America, which are composed of andesitic rocks. Crystals can accumulate on the sides and the roof of the chamber due to turbulence, so as this is mixing around, any crystals that form might stick to the sides, and therefore we can have a zoned magma chamber ultimately. One set of crystals out here that are layered on top of the initial crystals that formed early on. These are going to be made of a different chemistry than these. When we discuss forms of igneous intrusions, we're talking about the shape and the size of the intrusion. Starting with discordant intrusions, these are intrusions that cut across the grain. They cut across pre-existing structures within the rock. These include plutons, which are of any size, coming from Pluto from below. Batholiths being the largest, over 100 square kilometers in areal extent. Stalks are any discordant pluton that are less than 100 square kilometers. Dikes can be any size. Veins also any size, but generally smaller than dikes. Concordant intrusions, these are intrusions that run along pre-existing structures within the rocks, or bedding within a sedimentary rock, for instance, would include laccoliths. These are kind of like upside-down pie-shaped features, generally flat on the bottom and semi-domed on the top, so they squeeze in between layers of pre-existing rock and bulge it up a little bit. Sills are just like they sound. Just like a windsill, it's a flat surface, a horizontal surface, generally. So here we have a diagram that describes pretty much every major thing that can happen. We have, again, a batholith that may be a gigantic regional feature, a pluton, a smaller but still very large feature. Either of these can feed things like sills. Sills are flat-lying concordant intrusions, like a window sill is a flat surface. A dike is not flat. It can be the same shape as a sill, but it's not in the horizontal. It's some offset from the horizontal. So a dike is like a spike of an intrusion through previously existing rock structures. We can reach the surface in the form of a dike here that is going to grow into a previous layer of volcanic rock that has been eroded away in this case. So essentially what we have here is the interior structure of a volcano with the outer slopes erased. A good example is Shiprock, New Mexico. I rode through here maybe 2 years ago, and I'd hoped to get up close to get some good pictures of it, but there was some significant police activity. And by significant, I mean hundreds and hundreds of people engaged in something. On all the roads, everything was shut down. I decided to detour. This is what I would have seen. I've been here before, but I didn't have a decent camera. So here we have the original neck of the volcano, perhaps, and then radiating dikes that emerge like spokes of a wheel from this hub. Now we can have ash falls and pyroclasts accumulate to considerable depth. That was probably the case here. It's all been erased because this is easily weathered. Again, dikes are going to cut across layers of country rock, where sills conform to the layers of country rock. Batholiths, again, are the largest forms of plutons, covering at least 100 square kilometers. Here we have a couple images from the Absarokas in northern Montana. We have a sill here. Again, this is going to run concordant with the original country rock. And then down here we have a dike which cuts across the original bedding layers of the country rock. A batholith, the Sierra Nevada mountains, and in this case Yosemite Valley, is going to be a dissection, a look inside a batholith. It's looking from the other side. This is Half Dome. You saw it in the previous image here. So this next image is going to be behind El Capitan here. This is granitic felsic rock, and because you're far enough away, you can't see the individual crystals, but you can get a feel for the lightness or darkness of the rock. This would be a very felsic, very light-colored igneous rock. Lots of orthoclase feldspar, lots of sodium-rich plagioclase feldspar, lots of quartz. Now, you probably haven't heard of this. This is another valley nearby called Hetch Hetchy. It was considered to be as beautiful as Yosemite, but it was close enough to the city of San Francisco that somebody got the idea of plugging it up, filling it with water, and building this. There's an O'Shaughnessy Dam located just outside of this upper left image. So this is what the valley looked like before. This is what it looks like now. There's an active environmental operation to try to remove the dam and return the valley to its present appearance. But there are a lot of people that argue against it because they want water. Now, when we talk about magma intruding into overlying rock, we have to think about what happens to the overlying rock. It doesn't just dissolve and go away. Some of it does dissolve and become part of the magma chamber. Some of it breaks off and ends up as a xenolith. Xeno meaning strange, lith meaning rock, just like xenophobia would mean a fear of people, strange people. Here we have a xenolith. So these xenoliths are going to break off, and sometimes we see these in cross sections of other rock, and we can tell therefore what the original country rock was and get a feel for the chemistry of the rock that formed around it. When we talk about igneous processes and plate tectonics, we need to think about magma factories. Plate tectonics drives magma factories. They form spreading centers, plate tectonics form subduction zones, and mantle plumes. When we talk about igneous processes and plate tectonics, we can divide these up into four major categories. We have ocean-ocean convergence exhibited in island arcs, like those of Indonesia, spreading centers, like that exhibited in Iceland, near the Thingvellir in southeastern Iceland, hotspot volcanism, such as that produces the islands of Hawaii, and ocean-continent convergence, where we have the buildup of mountains like the Cascades in the US, the Andes in South America, and so on. Starting with ocean-ocean convergence, we generate mafic to intermediate intrusives through plutonism, things that happen below the surface, mafic to intermediate extrusives emerging from volcanic events. In the case of the island arcs of Indonesia, the viscosity of the mix that generates this material is such that we can generate very, very explosive eruptions that led to The Year Without a Summer in 1816 and the writing of the novel Frankenstein, associated with the gloomy, dreary weather of The Year Without a Summer. A volcano caused that, volcano in Indonesia. Now, if we move to the opposite end of the Earth, to the North Atlantic, Iceland, in this case southeastern Iceland, we can see a superficial expression of the Mid-Atlantic Ridge. You can stand here and put your hands on the European plate and the North American plate, if your hands are as far apart as my hands anyway. Hotspot volcanism generates the Hawaiian Islands, and it's also responsible for the volcanic activity in Yellowstone Park. In this case, a mantle plume, hot rising material from the mantle, is moving through the crust, or the crust is moving over the mantle plume. So the mantle plume itself is moving or the crust is moving. Either way, relative to one another, they're moving. The oldest Hawaiian Islands are way up here, the Emperor's Seamounts. The youngest Hawaiian Islands are down here, being formed today, literally today. That activity in the middle of the Pacific is going to generate basaltic intrusives and basaltic extrusives because the chemistry of the mantle is basaltic, the upper mantle anyway. And lastly, we have ocean-continent convergence, which is going to generate mafic to intermediate intrusives and mafic to intermediate extrusives. Our example here, the west coast of the U.S., the Farallon Plate and the Pacific Plate are being subducted beneath the North American Plate, and the result is andesitic rock coming from an andesitic or intermediate melt. These produce fairly violent eruptions. Mount St. Helens erupted in 1980, scared a lot of people, killed, I think, 47 or 49 people, something like that. In South America, devastating volcanic eruptions occur regularly. What is the origin of the magma in magma factories? It can come from decompression melting in spreading centers. It can come from fluid-induced melting in subduction zones. There's a difference here. As pressure is removed at a spreading center, the rock will melt merely because the pressure on it is reduced. It's easier to go into liquid phase when that pressure is removed. When we add some water to the material in a subduction zone, we also can induce melting. The mere presence of water will lower the melting temperature of rock. So we can see that here. We have hot mantle material starting out as peridotite that is rising into the crust. So this peridotite is migrating through a gabbro. It's going to be picking up some of this gabbro material and precipitating olivine crystals. Those olivine crystals are going to produce a peridotite layer here. If the magma works its way up into the ocean crust itself, it's going to produce a series of sheeted dikes. Lots of dikes, billions and billions and billions of them, are going to be fused together, forming new ocean crust. As that new ocean crust cools and moves away, it's going to be covered with sediment. Dead plants and animals falling from the ocean above, mixed with whatever creepy crawlies are moving around the sediment below. So this thin dike, as it's forming, is going to look like toothpaste coming out of a tube. And the result is, as it solidifies, are pillow lavas. So we have dikes intruding into other dikes, which are going to be intruded by more dikes, and ultimately fuse together to form the ocean crust. So these all come together eventually. Again, sediment will be deposited on top and move away. The further away you get from the spreading center here, the thicker the sediment. The gabbro layer is going to metamorphose when it contacts the magma. It's going to be heated up and converted into different crystals. These sheeted dikes now provide a conduit for water, and this water, as it travels through the sheeted dikes, starts out cold. It's going to get heated up, and as it gets heated up and travels through these sheeted dikes, it picks up more and more ions, cations and anions. Eventually it's going to rise to the surface of the crust and blast out into the deep water where it's cold. It's going to go from 400 degrees or so centigrade to 2 degrees in literally seconds. As it does cool off in seconds, any dissolved ions that are precipitated beyond saturation for those ions are going to be accumulated as crystals. They're going to precipitate immediately in the water column and fall to the ocean floor. Whereas in the magma chamber, again, we're going to have olivine crystals forming, dropping down into a peridotite layer, and therefore generate a layer of olivine crystals. This is what happens when hot water full of ions enters cold water, also full of ions, but not quite as full. You get the precipitation of these minerals from what are called black smokers. Okay, now let's take a sediment sled ride down into the asthenosphere. We're going to start out with ocean sediment accumulating on the seafloor here on the basaltic oceanic crust. This material is going to approach the subduction zone here, and as it begins to subside, as it begins to travel downward into the Earth's crust, it compresses this sediment into an accretionary wedge that eventually gets pulled along, dragged down into the asthenosphere. Now what's happening is this subducting ocean crust carrying the sediment with it also carries water with it. We have sediment grains with interstitial seawater. This is a very corrosive liquid, far more corrosive than fresh water. This water is going to be trapped as the pressure and temperature increase as this material is being subducted. Ultimately, this trapped water is going to be released and it joins the melt here. This is going to cause sedimentary rocks to melt at lower temperatures. Now, it's not quite an accurate analogy, but in a thought process kind of game, it works. This is a bit like adding more water to a block of salt. You're going to increase the ability of that salt to dissolve. In this case, the addition of water is going to increase the ability of the ions that make up crystalline rock to separate, to come apart. So the water provides a conduit for the separation of that crystal lattice, the freeing up of the material into the liquid phase. So a change from solid to liquid phase is accelerated and accentuated by the presence of water. This water and molten sediment are going to rise buoyantly. Remember, crustal material is much less dense than material below the crust. So any melt of crustal material is going to result in blobs that are going to rise through the crust because of their buoyancy. Ultimately, molten sediment combines with lithospheric magma, and this becomes our initial melt chemistry. In this case, an andesitic mix, most likely, that's going to result in this island arc andesitic volcanic chain. Once this material reaches a critical state, we can have an eruption, and in some cases, a very, very large eruption. One such very, very large eruption is the eruption of Toba in Indonesia. Back in 1993, a journalist proposed that the most recent Toba eruption, the youngest Toba eruption that took place around 75,000 years ago, plus or minus 900 years, was responsible for a genetic bottleneck that nearly wiped out our species, Homo sapiens. The genetic evidence suggests that around that time, the human population was reduced to 10,000 individuals, and that everyone that has emerged since then, all the differences in hair color, skin color, height, weight, all features have evolved since 70,000 years ago or so. There is some evidence for that genetically, that it occurs in other animals as well, but some East African data suggests that it wasn't really a big deal. Some Indian data also suggests that it wasn't such a big deal, and so on as we look around the world. It's still a good idea, but it might not hold up. Now, the reason this idea was proposed was not just because of the genetic information, which is likely valid, but because of the eruption, the magnitude of the eruption itself. It blasted about 3,200 cubic kilometers of material out of the caldera, and the ash that was emitted was sufficient to cover all of Southeast Asia by 15 centimeters of ash. That pyroclastic debris covered the whole region. It's been found all around the world. Everywhere we look for it, we see it. So it was a global event. And it's thought, based on its size, about 12 times greater than the Tambora eruption that led to the year without a summer, that this eruption resulted in a 6 to 8 to maybe 10-year volcanic winter. Again, there's some evidence for that, but there's also evidence against that. So the jury's still out. We'll get back to that when we cover volcanoes later in the course. So for now, we're going to end igneous rocks here, and we'll pick up with sedimentary rocks next.